Simple harmonic motion is a type of motion that can be represented with a sine wave. And if we were to graph a sine wave and call this axis position, and then make this axis out here time, we have now graphed simple harmonic motion. There's a couple physical situations that show simple harmonic motion. One would be a mass attached to a spring allowed to vibrate. The other might be a pendulum. But right now we're just going to focus on the mass attached to a spring. So if I had a mass and I attach a spring to it and maybe fix one end of the spring to something that's not going anywhere, everybody I think could imagine that if I push the mass to one side and let go, it'll vibrate back and forth. If I were to graph the amount of displacement from a place that we call x equals 0, the equilibrium spot, we would see this sine wave up here. Before we get into notions of the period and frequency of this vibration, we have to backtrack a little bit to the reason why springs exhibit this kind of behavior. Turns out you get this kind of motion when you have a situation where the force that is exerted on the mass is proportional to the position. And springs follow a law known as Hooke's law that says that the force is equal to a constant times the displacement. And there's a little negative sign out front because if I push a spring, say, to the left, the force it exerts will be to the right. So the displacement and the force will be in opposite directions. The spring constant, which is what this K is a measure of how strong the spring is. Big K means a spring that can exert a lot of force for a little bit of displacement, and a small K will exert very little force for the same amount of displacement. You will do a few problems just plugging numbers into this, but this does follow the pattern that allows us to characterize this as simple harmonic motion. The period, which is the time it takes for this spring to vibrate back and forth once in this situation, is given by the equation 2 pi times the square root of the mass of the system over the spring constant. So a big mass is going to have a lot of inertia, and it will take longer to go back and forth once. So big mass will give us a bigger period. A stronger spring will have the opposite effect. It will cause it to vibrate back in a smaller amount of time, and these are the only two factors that affect this. Now, we learned in our conceptual videos that frequency is the inverse or the reciprocal of the period. So if we wanted to rewrite this equation in terms of the frequency, we would just invert the whole thing and we get something like this. But this is the basic equation that we tend to use most often. All you're going to be asked to do in this worksheet is manipulate these formulas. Most of the rest of it is common sense and also little tidbits that you picked up by watching the conceptual videos.